here we are trying an example of angled launch. This is the signal flare example, so let's read that one quick. So a pistol that fires a signal flare gives it an initial velocity, a muzzle velocity of 125 meters per second, an angle of 55 degrees above the horizontal. You can ignore air resistance and find the flare's maximum height and distance from its firing point to its landing point when fired on the level salt flats of Utah. Okay, so in doing this problem, let's just make clear that you probably want to shoot that flare a little more straight up rather than way off to the side. But regardless, also there is going to be air resistance, so the numbers we come up with here aren't going to be very realistic for this situation. So let's just keep that in our back of our head as we solve this one. All right, so I have a drawing here of what we're going to look like. So the first thing we want to know is how high does it get? So in other words, the higher it is, the further away people can see it. Okay, cool. So in order to set up a max height problem, we're going to identify our problem type. So I know it's moving in the X, and as soon as it's fired, it's only under the influence of gravity. So I have a 2D motion problem. That's projectile motion. So I list my two sets of variables, and I identify its projectile motion. So I automatically know the acceleration in the X is 0. The acceleration in the Y is negative 9.8 meters per second squared. These two velocities are the same, and if acceleration is 0, I'm using equation number 2. Now the next thing I know is this is an angled launch problem, which means I need to resolve the initial velocity into its components. So let's go ahead and do that. So this side down here, adjacent to the angle, so we're going to be using cosine, so ka toa, a h. So adjacent to the hypotenuse, I'm going to use cosine, so this one is going to be 125 cosine of 55. The y one is opposite, so that's going to be using sine. So this one comes out to be 125 sine of 55. Don't bother typing these into your calculator. Leave them like that. We'll put them in just like that over here. So 125 cosine of 55 and 125 sine of 55. Now, we are trying to find max height. And whenever we try to find max height, yes, the vertical velocity reaches 0 at the top. There is a horizontal velocity when it reaches the top. It's still moving sideways. It doesn't change its velocity at all during this whole time in the horizontal direction. But in the vertical direction, it does reach a vertical velocity of 0. All right, we get to choose where it starts. I'm going to like to choose this point as x equals 0 and y equals 0. Okay. And our goal is to find the maximum height here. Well, that's kind of nice. I just could pick an equation without time. I have everything else. Did I need to do anything at the x direction, max height situation? No, I didn't. How cool is that? All right, so let's go ahead and solve that. So we're going to pick an equation without time. Equation number 3 will do good there. So vy squared equals v naught y squared plus 2ay times y minus y naught. Make sure when you write out these equations, you are writing those subscripts. They are important because if I accidentally just write v naught, I might go, oh yeah, v naught's 125. But no, this is v naught y. That's got to be 125 sine of 55 I got to put in there. Okay, so let's cross out that's 0. All right, and we're solving for this y. So we're going to move this v naught y over to the other side. So I'm going to have negative, and I might as well substitute in while I'm doing it. So I have 125 sine of 55 squared. Okay, so when I moved it over to the other side, it became negative, equals my 2ay times y. So I'm going to divide that 2ay over. So I have divided by 2 times negative 9.8 will give me my y. And so the maximum height this reaches is it gets up to 535 meters high. Now again, air resistance, that number will be considerably lower. All right, so that was kind of cool. When max height came along, I didn't even have to do the x direction. So maybe if I was wary enough, maybe I wouldn't even bother writing that down. All right, time in the air. Okay, so this is our part B. It wants to know how far in the air or how long in the air and how far away. And this distance here, this right here is known as the range. Okay, so we're going to be finding not only the hang time, I guess you would call it, but also the range. All right, and you'll remember that these two times are the same. So if we find the time in, say, the y direction, I can use that time in the x direction. Or if I find the time in the x, I can use that in the y. All right, so let's get started with what we know. So we know that it starts at a height of 0, ends at a height of 0. So this is a y naught equals y problem. All right, it was also an angled launch, so this number here is from my resolved V naught over there. So I have 125 sine of 55, and this one is 125 cosine of 55. I'm going to choose it to start at x equals 0 as well. All right, let's see if we can use our tricky tiger trail here. So if the initial velocity was positive 125 sine of 55 and it starts and ends at the same height, yeah, my final velocity is going to be negative 125 sine of 55. Now, if we didn't use our tricky tiger trail, that's all right. We can still solve this problem without it. So let's kind of try that just in case we didn't catch on to that. So if I want to find the hang time, I'm going to pick an equation without y. So let's go ahead and do that. So I'm going to pick pick an equation without Vy. So I'm going to pick equation number 2. Yeah. So I have y equals y naught plus v naught yt plus 1/2 ayt squared. Crossing out the 0. And you'll see that I got the t and the t squared. Excuse me there. And so what we can do is we can make our substitution. So I see 125 sine of 55 times t plus 1/2 ay, which makes it negative 4.9 t squared. So what we have to do is we have to factor out a t. So we lose one t, and that becomes the t equals 0 term. We then can solve this equation for t, and so I end up with negative 125 sine of 55 when I move it over to the other side, divided by my negative 4.9 equals t. And so we plug that into our calculator. We get a time of roughly 20.9 seconds. So when you fire that flare up in this case, it's only in the air for 20 seconds or 21 seconds. So if someone's not looking at that 21 seconds, you're out of luck, I guess. But remember, these times are the same. How cool is that? So now I have 20.9 over here. That means I also have 20.9 over here. So I can go ahead and solve for this x value. All right, so let's try that. So now I have x is equal to v naught x, which was my 125 cosine of 55, times the time, which I just found over there, 20.9, to give me an x value of 1498, so about 1,500 meters. It's about a mile. We're real close to a mile away that flare is landing. Ideally, you want to shoot that flare more straight up so people go, oh, there's the flare, and they only saw it part way up. They can go, oh, probably shot it straight up, so it's landing right where they're at. So they can maybe find you a little better. Also, you could tamp out whatever forest fire you decide to start, but we're on the salt flats of Utah, so we should be okay. All right, so there's our example. A little extra there for you though, but there you go.